We're going to learn some analytic methods today. So for a single first order differential equation, just one differential equation, in chapter 1 we developed 3 different analytic techniques for how to solve it, and they were very specialized and they only applied to certain kinds of differential equations. We had one if it's separable, so that's sort of like my favorite, and then we had 2 others for when you have a linear differential equation, linear first order. And it was the lucky guess or undetermined coefficients and integrating factor. So for a system of first order differential equations, the analytic techniques are even fewer and even more limited in what you can apply them to. But we are going to study some of these special techniques because they can offer us insight and intuition into the behavior of solutions when you're studying a system for which there are no analytic techniques. So first, remember that even though finding solutions can be hard, once you have a candidate for a solution, we can pretty easily check if it really is a solution. So this is important because it can help us check when we've done like pages and pages of algebra to try to come up with a solution. We can always check and see if it's right. And it's also important because many of the techniques we develop are really just sophisticated guessing. Right? We just guess and then check if it works. So we're going to do a little example where we just check if this is a solution. So I have x prime is negative 5x plus 4y, y prime is x minus 2y, and I've got 2 functions, x of t and y of t. I've written in vector notation. So this is my x of t function, this is my y of t function. I want to know if this is a solution to the system. So if it is a solution, then x prime has to equal negative 5x plus 4y, and y prime has to equal x minus 2y. So I'm going to write x equals 5e to the negative 6t plus e to the negative t. Y equals e to the negative 6t plus e to the negative t. So those are my 2 functions, x and y. Those are my candidates for solutions. I need both these 2 equations have to make my differential equations true. So let's start with the x prime equation. So I need to know what x prime and y prime are, so I might as well just do those now. So x prime, the derivative would be negative 30 e to the negative 6t minus e to the negative t. Just take the derivative. And then y prime would be negative 6 e to the negative 6 e to the negative 6t minus e to the negative t. So I have x and I have y and I have x prime and I have y prime. I need to see if these equations are true. Okay, so I'm going to write my first equation down. X prime has to equal negative 5x plus 4y. All right, so x prime is this equation. I'm just going to make a substitution, replace x prime with this expression, negative 30 e to the negative 6t minus e to the negative t. And the question is, does that equal negative 5x plus 4y? So I'm going to replace x and y with what they're equal to. Just make a substitution. So I have negative 5 times x, which is 5e to the negative 6t plus e to the negative t, plus 4 times y, which is e to the negative 6t plus e to the negative t. So when I simplify the right-hand side of this equation, I want to see if it equals the left-hand side. If it does, then I can move on to check my other differential equation. Right? Not necessarily a solution yet, but let's see if it's equal. So this comes out to negative 25 e to the negative 6t minus 5 e to the negative t plus 4 e to the negative 6t plus 4 e to the negative t. So no, because I've got negative 25 e to the negative 6t plus 4 e to the negative 6t is negative 21 e to the negative 6t. Yeah. So it turns out this is not equal, so I do not have a solution. Okay, so this candidate that I thought what might be a solution is not. So I don't even have to go any further. I don't have to check y prime. I already know it's not a solution. Yep. 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 So you're given the differential equation, you're given a candidate as a solution, and we're just checking to see if it's really a solution. Yep, all I plugged into was x prime. If that worked, I would have moved on to check y prime, and if that worked, then I would say yes, it's a solution. But x prime, this equation for x prime is not true with this x and y candidate. All right, so here's another candidate. X of t, y of t. Is this a solution? You guys can work on this one for a minute or two. Okay, so let's see. X of t is going to be negative 4 e to the negative 6t, and y, plus 5 e to the negative t. Y is e to the negative 6t plus 5 e to the negative t. So that means that x prime is 24 e to the negative 6t minus 5 e to the negative t, and y prime is negative 6 e to the negative 6t minus 5 e to the negative t. So now I know x and y, I know x prime and y prime. I'm just going to plug everything I know into my two equations and hope that they are true. Okay, so I'm going to write down my equation x prime equals negative 5x plus 4y. And then I'm going to substitute in expressions for x, for y, and for x prime. So I have 24 e to the negative 6t minus 5 e to the negative t. Does that equal 5 times x, and replacing x with negative 4 e to the negative 6t plus 5 e to the negative t. Thank you. Plus 4 times y, which is e to the negative 6t, plus 5 e to the negative t. So now we try to simplify the right-hand side and hope that it equals the left-hand side. So this comes out to 20 e to the negative 6t minus 25 e to the negative t plus 4 e to the negative 6t plus 20 e to the negative t. So I get 24 e to the negative 6t, and negative 25 plus 20 is minus 5 e to the negative t. So it is equal to that. So the x prime equation is true. Right? Now we have to check the y prime equation. X minus 2y. Okay, so y prime, that's negative 6 e to the negative 6t plus 5 e to the, nope, minus 5 e to the negative t. Does that equal x, which is negative 4 e to the negative 6t Thank you. And what's y? Thank you. All right, so now we try to simplify the right-hand side, see if it equals the left. If it does, then we really have a solution. Negative 4e to the negative 6t plus 5e to the negative t minus 2e to the negative 6t minus 10e to the negative t. So negative 4, negative 2 is negative 6. And 5 minus 10 is negative 5. So yes, it is equal. So it's a solution. All right, I saw some people working on this one. Are you finished or? Nope, this is another one. Practice. It's a different system, different possibility for a solution. Same approach. The only thing is you have to also make sure that x of 0 equals negative 2 and y of 0 has to equal 0. So we've got initial conditions, negative 2, 0, x and y. So the easiest thing to check are the initial conditions, right? If x of t is 5e to the negative 4t and y of t I have to check that x of 0 is negative 2. When I plug in zeros here, I get 5 minus 1, which is 4, which is not negative 2. So done. Yeah. This is actually an example from your textbook, and I copied the solution wrong. So I meant for it to be one that works, but oops. It's the x of t one is wrong. It was I can't remember what it was. Y of t is right, but x of t isn't. In the book, yeah. No, I copied the x of t solution from the book wrong. Okay, so we're going to study now a way to come up with candidate solutions. Okay, rather than say pulling them out of thin air and checking whether they work, we're going to try to come up with a way of generating solutions. So a special kind of system is called is this decoupled system. A decoupled system is one where the rate of change of one or more of the dependent variables depends only on its own value. So like dy dt will only have y's in the right-hand side, and dx dt would only have x's on the right-hand side. Okay. If this is the case, then we can just use techniques from chapter 1. It would be a system, yeah. Like I could have, yeah, yep, or decoupled is the word, yeah. But they're totally separate. They don't, the two terms don't interact. Which or the two dependent variables don't interact. And when they do interact is when we get the most interesting phenomena. But for a totally decoupled system, there's no interaction. So that would be like this case. Okay. So if x prime is negative 2x and y prime is negative y, we can solve each of those equations independently of the other. So we could use separation of variables. We could use any of the techniques from chapter 1. So if dx dt is negative 2x, then 1 over x dx equals negative 2 dt. Just separate variables, integrate, and we get the ln of x is equal to negative 2t plus c. Raise e to both sides. Oops. And then I'll do my little trick where the e to the c becomes its own constant, k. So x of t is going to become k e to the negative 2t. And they did give me an initial condition. X of 0 is 1. So x of 0 would be k, which is 1. So we know k is 1. So my final formula is e to the negative 2t for x of t. So nothing new here, right? These are just two. It's a system, but it's decoupled, so we can solve each one separately. It can still be a system. You can still have interaction is not required to have a system that don't interact. Yeah, right. Yeah, exactly. It'll be like predator and prey that don't interact. Yeah. So it's not the most interesting system. Yeah. So then we could do a similar thing for y prime equals negative y. The solution to that guy would be k e to the negative t. Yep. And then y of 0 is 1, which means that k is 1. So from here to here was separation of variables. Just did it in my head. So we love it when they're decoupled, right? Because we have this really simple, you just use what we already know. And sometimes we will get a system that's called partially decoupled, which means one of the equations depends only on itself, and the other equation depends on both dependent variables. So we do have some interaction in this system, but one of them is dependent only on itself. So we can solve that one right off the bat, right? I can start with dy dt equals negative 4y, and I could solve that by separation of variables. So I would get y of t equals k e to the negative 4t. And then they did not give me an initial value yet, so we'll just leave it like that. We'll call this k1. And I'll use, anytime I need a constant, I'll use k and number it. So I have a general solution for y. Now I need to find a general solution for x, right? So I've got dx dt, which is 2x plus 3y. But now I have a formula for y, so I can put that in here. So I'm going to have dx dt is equal to 2x plus 3. I don't really need parentheses. Times k1 e to the negative 4t. Yes. So I think what you're thinking of is one of the principles of linearity. This is a linear system. This is a special linear system where we have a of t times x plus b of t, right? So this is a non-homogeneous linear differential equation, which we have two techniques for solving. The lucky guess, or undetermined coefficients, and integrating factor. So let's use linear, which is what I think you were just suggesting, where you lop it off. Yep, you got it, yeah. So the linearity one, if you remember, says you need a general solution to the homogeneous equation, which is pretty easy. That's where you just lop off the b of t. So we would just need to solve dx dt equals 2x. Not too difficult. Okay. And then step 2, we need one specific solution to the entire ODE. So this is where we use lucky guess or undetermined coefficients. And then step 3 is if you add what you get for step 1 and step 2 together, that's your general solution. So this is one of our methods of finding a solution to a non-homogeneous linear differential equation. So step 1, pretty easy. Let's do that first. dx dt equals 2x. We have to solve. So that would be x of t is e to the 2x. T, thank you. Yeah, and there's a k in front. We'll call it k2 e to the 2t. So there's my solution to my non-homogeneous, sorry, my associated homogeneous linear equation. K2 e to the 2t. All right, so now we have to find a particular solution to the non-homogeneous differential equation. This is where we do some guessing. So 2x So it helps, remember, when you're doing your guessing, to move the 2x to the left. So we would have dx dt minus 2x equals 3k1 e to the negative 4t. So the reason it helps is because you say, okay, I'm looking for a function who, when I take its derivative and subtract 2 times itself, I end up with a multiple of e to the negative 4t. So what kind of guess? E to the negative 4t with maybe a coefficient in front. Yeah. So I'll use alpha e to the negative 4t. Okay. Alpha yet to be determined, right? We're going to figure out what kind of what alpha will make this work. Okay, so that means that dx dt, well, I'll just plug it in here. So now I'm just going to plug in x and dx dt. So dx dt would be negative 4 alpha e to the negative 4t minus 2x, which is 2 alpha e to the negative 4t. Plugged in x prime here, plugged in x here. I need to try to force this to equal 3k1 e to the negative 4t. So this is negative 6 alpha e to the negative 4t, because those are like terms, equals 3k1 e to the negative 4t. Yep, lop off the e's. I can divide them out because e to the something's never 0, so I can just get rid of those, right? So negative 6 alpha has to equal 3 times k1, which means that alpha, yep, negative k over 2 or negative 1/2 k. So I found a particular solution. My particular solution is going to be x of t equals negative 1/2 k1 e to the negative 4t. So go back to my list of steps here. I got this. Negative 1/2 k1 e to the negative 4t. And then finally, my general solution is the sum of my two equations from step 1 and 2. So that would be final x of t is k2 e to the 2t plus, I know, sorry, minus 1/2 k1 e to the negative 4t. So there's my x of t, general solution. And my y of t, remember, we already found, because that one was easy, because that one was totally dependent on itself. So I have an x of t and a y of t. That's the solution to a system. You have two functions, x of t and y of t. Yep. Yep. Yeah. So next, now that I have a general solution for x and a general solution for y, now if you're given an initial condition, you can plug in and figure out what k1 and k2 have to be. Got it? Okay. So let's see, my x of t was, can somebody read it back to me? K2 e to the 2t. Okay, and then y of t was what? Good. Okay. So now this is my solution, my general solution to the system. Now I use x of 0 and y of 0 to figure out what the k's have to be. Okay. So y of 0, I'm starting with y because it only has one constant in there, so I can figure that one out first. So y of 0 would be k1, which is 1. Okay, so I know k1, and then x of t, x of 0, would be k2 minus 1/2, because I'm plugging in a 1 for k1 and a 0 for t, so I just get 1/2 for that term. And x of 0 is 0, which means that k2 has to be 1/2. So then you can just rewrite your solutions, plugging in the values for your constants. K2, so 1/2 e to the 2t minus 1/2 e to the negative 4t. And then y of t, k1 is 1, so it's just e to the negative 4t. Yes. Given in the question. Yeah. So there's not anything super new today, right? This is all just applying techniques that we already knew to special kinds of systems. Either fully decoupled, in which case you can just solve each one separately, or partially decoupled, where one of them's easy to solve. You solve it, and then you plug it back in and use another technique on the other one. All right, so here's some practice. Try this one in your groups. All right, so since I didn't give you the answers, let's go over it together. So one of these is easy to solve, right? Y prime equals 2y. You can solve with separation of variables, and it will come out to y equals k e to the 2t. And we'll call this k1. Okay. So y equals k1 e to the 2t. Done with half the problem, right? We have a solution, half of the solution, y of t. Now we just have to figure out x of t. So that one is a little bit harder, right? So now I rewrite my equation, x prime equals negative x plus 3, and instead of y, I put in the formula I just found for y, k1 e to the 2t. Now I use my properties of linearity, or the lucky guess procedure, to figure out an x of t. So I start by solving the associated homogeneous equation, right? X prime equals negative x. That's not too bad. That comes out to x equals k2 e to the negative t. Some other constant, different from the first one, e to the negative t. Okay, so step 2, I need a lucky guess. I need to find a particular solution that satisfies the entire differential equation. I move the x over because that helps me think about what my lucky guess will be. I need a function whose derivative plus itself equals 3k e to the 2t. So what could I guess? Alpha e to the 2t. So e to the 2t makes sense because I want to add a function's derivative plus itself and get something e to the 2t. And when you take the derivative of e to the 2t, you get 2 e to the 2t. So the e to the 2t stays preserved, which is why that guess makes sense. So now we plug in our guess. X prime would be 2 alpha e to the 2t plus x, which is alpha e to the 2t. And we're going to force this to equal 3k e to the 2t. Choose alpha in such a way that they have to be equal. So this is 2 alpha plus 1 alpha is 3 alpha e to the 2t, has to equal 3k e to the 2t, which means alpha equals k. And I stopped writing the subscript in my k's. K1, yep. This is an easy thing to forget. K1, K1, K1. Okay, so alpha has to be K1, which means that my actual solution, my particular solution, is going to be x equals K1 e to the 2t. So I have my homogeneous solution, my particular solution, add them together, and you get the general solution for x of t. So it's k2 e to the negative t plus k1 e to the 2t. General formula for x of t. Everybody okay with it? Okay. All right, so now we just use our initial conditions. K2 e to the negative t. And y of t was k1 e to the 2t. All right, so y of 0 has to be 0. So y of 0 is k1, which has to be 0. And if k1 is 0, that means that y of 2 is just the constant function. Sorry, y of t is the constant function 0. So y of t equals 0. And then if x of t, x of 0 is 1, x of 0 would be k2 plus plugging in k1, which is 0. That means k2 has to equal 1. So my x of t solution is going to be e to the negative t. And k1 is 0, so that term goes away. That's it.